सर जी स्टार्ट कीजिए सर।
Okay. Uh, so this is the introduction session for the subject mechanical behavior of polymer and composite. And in this introduction session, we will discuss the doubt that will comes from quizzes that numericals you has to be solved in quizzes, and some related query that you wish to know that about the end-term exam or anything else. So we will solve this. And apart from that, if you have any problem, like if you have any theoretical problem while attending the lecture, so you can post your question in the question answer forum. So that can be helpful for both as well as you as well as other students whenever they reach there and saw the question and the solution for that. So most of the people used to do that. So if anyone has, they can post that. And so here now I'll start from quiz one. So anyone of you has any question, you can comment that question in the YouTube comment box. It's live on the YouTube. So then we will move forward. So, so if I'm talking about the questions like I'll start from quiz one. Okay. So the from quiz one, most of the question are theoretical. That's directly come from the PPT or the lecture of the professor. There you can just visit. It's called the lecture, and you get most of the answer. Not most of the, even all the answer except the one numerical that I mentioned in this. Like in the quiz one, there was at question number 10 is the numerical that polymer with a degree of polymerization of 1200, 1200 will have a molecular weight of. So such kind of problem you can solve, like we know the formula for the degree of polymerization and the molecular weight. So as we know, like total molecular weight is equal to degree of polymerization into molecular weight of that monomer. So, so if I'm talking about that specific question, in that question you have, you know, the degree of polymerization is given 1200, and you know the molecular weight of polyethylene. That's you can get easily by like from carbon and hydrogen add up, you get equals 28, and by using this formula you can get the answer for this question. And similarly, if in quiz one we are talking about the question number 12, this is not actually a numerical, but it's a general answer like the glass transition temperature in degrees of rubber is approximately. So it's come from data that the professor provided in the PPT. That was not exactly, it's approximately answer of that question. And there was one important question, like when the professor was talking about the glass sensing temperature. So this is it's a bit similar like the melting point of the material. Like if I'm talking about, everyone knows that above the temperature, material behave as a solid because it's melt out, and below that's very hard brittle. They have very brittle. So similar kind of things happen in the polymer, but here the difference is here we use the term for that is glass sensing temperature instead of melting point temperature. Cause the another difference in that is that like melting point is we know it is specific temperature for something made at this temperature, something is brittle before that, and it's become fluid after the temperature. Like if I'm talking about the non-metal, like a simple example we can take for ice, like at 0 degrees Celsius. Below that, zero and below that, it's like if water become ice, it's become hard, and above that, it's behave as a fluid. So similar things not happens with the polymer. In polymer, what happens like there was a range of temperature at which the volume decreases rapidly, not sharply. So that happens. So whenever we have to know like the any polymer that how it will behave. So it depends upon what's the glass ceiling temperature of that polymer and what's the operating temperature at which we are talking about. I have also given a question in the quiz number one that here we were asked about like there was a glass sensing temperature is -50 for the polymer. So how it will behave. So if I'm talking about the how it will behave at room temperature, obvious, because its gas transition temperature is minus 50. And room temperature generally 28, 30, 40 approx. Look, this is the temperature that there is room temperature sense. So it's uh, quite bigger than you can see gas temperature. So obvious metal behaves like rubbery or it depends upon polymer to polymer. But below that temperature, it behaves as a dip. So in our case, like also we have asked one question, page number one, that gross technical temperature of the rubber is minus 70. The same thing, like when everyone has used the rubber for its full life, and still we are using to erase something or in multiple places. So it's very soft. Just cause of its glass transition temperature is minus 70, and the time temperature we are operating is quite large from that. So that's the reason it's become soft. If you will go below minus 70, then you feel that it's to act as a hard plastic. That's the reason. So if anyone need any question, then you can ask. Okay. So if any one of you face any problem in any question of the quiz number one, so we can discuss that. And otherwise, we'll move forward to the quiz number two. Okay. So in quiz number two, once we start, like initially we give a question where we provide a modulus and normalized temperature graph. And here we are talking, we have a mark for different region and asking about their name. So it's very simple, like Professor mentioned this question, and for that you can go the lecture of the professor at DC, and then it's a tutorial. PPT is available, types available. You can get a very better understanding of this by scrolling there. Okay, and also when we are talking about classy region, that like if I'm talking about like we know it's look like in this way. Just second. So somehow it looks like this, but in this way, not exactly, but somehow it looks like this, as I mentioned. And here we have these two loose sides. So this is actually count. This is something that glassy region, and the reason is that like for example, if I'm talking about if you have a polymer that's made of multiple threads, anything, and we are stretching it. So few of them just broke. So suddenly its models drop, then constant suddenly drop. So due to that, we get this. And there is other reason like this region we mentioned. This is your viscoelastic transition region, and if I'm talking about this third one, this is the rubber region, and the last will depend either is viscous region or David Bernal. It depends upon what's the polymer is. Either it's polymer, thermoset, or thermoplastic in that way. तो उसने बोला कि स्टार्ट करो यूट्यूब पर आओ ना तो मैं प्लीज ओके सो दैट प्रॉब्लम okay. So from the quiz one and two, most of the questions like theoretical, it's available in the tutorials. You can scroll and get. So in quiz two, there was a question of total strain. So as you know that the total strain, just give me a second. I'll have to erase this so that I can. So as professor mentioned this formula. total strain is E1, this is the modulus plus 1 minus E2. So, in the question, I mentioned that few percent of covalent bond and few percent of secondary bond. So, F is the percentage of the covalent bond, and 1 minus F we can the percentage of secondary bonds. And here E1 and E2 are the young modulus of covalent bond and secondary bonds. And sigma is the applied distance. So from this formula, you can easily get any problem related to the total strength. That's you can solve easily by the given data. And this formula is also mentioned in the tutorials of professor. Oh. There was one more question like we have mentioned, and we give you a ratio of working temperature versus glass transition temperature, which you know is like normalized temperature. So what is actually PG is the glass transition temperature of the polymer and T is the operating temperature. So if the both temperature are same, then this issue counts to one, and at that instance, polymer behaves rubbery, leathery. So once you go below to this, that means your operating temperature is lower than your gas transition temperature. So that time polymer behave uh, as a hard plastic in that way. And if you go above one, that means operating temperature is greater than your gas transition temperature. So that kind of behave as a rubbery or depends upon how far your temperature, operating temperature from the gas transition temperature. So up to this point, if anyone has any query or any question up to quiz 2, then he can ask. Because in quiz 1 and quiz 2, there are only one or two numerical in each quiz, and rest all are come from theoretical parts, and that's all available on professor's website, professor's tutorial and PPTs. So let's wait few minutes. So if anyone have any question, then you can ask. You can you can mention your question in the YouTube. It's also streaming live on the YouTube, so you can put your questions over there in the comment box. Okay, so now move forward to the quiz 3. In this quiz, we have more question compared to the previous slide, previous quizzes. So if I'm talking before the initial question, that can be easily solved because this belongs to a theoretical portion. And in that quiz from question number 11 to the last, you have numericals. So like if I'm talking about question numerical number 11 in the quiz 3. So here like it's mentioned Kelvin model with young modulus. Here you given E, young modulus. And the second is your is given in the question, is given in that question, and standard is also given 0.01 per second. And here he was asking you for the stress after 10 seconds. That is T equals to 10. So is it is very easy as it's mentioned that here we have to use Kelvin model, and we know the stress relationship in Kelvin model that is sigma of P equals to mu into standard plus E into strain. So everything we have known in this, we know E, we know mu, we know standard, and all. So we can use just put the values here and we can solve this. Okay. Any any question up to now? So similarly, we'll move to the another question. Uh, Question number two. Here we are asking for Kelvin Wilgott model. Okay. So in this question, we have given modulus, is given mu, is given to you, and it's also mentioned that it's subject to a constant stress of 80 megapascal. So yeah, the initial stress sigma naught is still given to you, and here they were asking for strain after 2 seconds. Okay, so you have to find out the strain after 2 seconds. So for this Kelvin bracket model, we have such data, we have to find the strain. So for that, in the code, we also has to be identified like what kind of problem is this either a load or relaxation, because in that problem the input is applied to the input is stress. So it's a problem come from heat load. So for that we know that how we have to solve this. We have formula like sigma t equals to sigma naught by E 1 minus E power minus T by tau. And this is uh, sigma naught we know it's given in the question, modulus is given in the question, and now I'm talking about the time t small t. So it's asking the question that you have to find after 2 seconds strain, and the thing is tau, it's time constant. So tau basically is equals to mu by e. So we know mu, we know e. So from here we can get and solve the answer of this problem. Okay, any doubt? Okay, so we'll move to the next question. So it's question number 13. Okay. In that question is mentioned that a Maxwell model exhibits state decay from 30 megapascal to 10 megapascal in 2 seconds. So in that question, we know the decay from one stress to another stress. Okay. And given time at which. So like in that question, we have to know if it's just decaying from 30 megapascal to 10 megapascal. So obviously the input stress is 30 megapascal. So sigma naught is given here, that is 30 megapascal. And he's talking about like in 25 seconds decay from 30 megapascal to 10 megapascal. So sigma, if I'm talking about the 30 megapascal at initial time t equals to 0, is that was just in 25 seconds, it will become 10 megapascal. Okay. Now, he was asking for find the relaxation time. Okay. So in Maxwell model, if we have no input stress and of for stress after some time and also involve the use of what we call relaxation time. So we know the formula for that. So in that we know everything like we know stress at 25 second as 10 amperes, sigma naught we know 30 ampere. Time its mentioned is 25 seconds. So from that we can get the value of tau here. And that will be your answer. Let's move to the next question of this. So in the next question, we are asking for like a polymer subject to a constant stress of 100 megapascal, exhibit a strain of 0.2 after 6 seconds, and determine the creep compliance in megapascal units. Okay. So in question number 14, stress is given to you, strain is given to you. So it's very easy formula available for creep compliance. So you can just put your values in that formula like counting of your creep compliance equals to sphere times. So we know stress, and from here we can get your answer. So and the question number 15, actually this question also solved by the professor in the tutorial. In that question, like he was asking, no, he was not that solved, but he give you some situations related to this question. Like in this question, we are asking for a like for a unit value of the ratio of applied stress and the elastic constant of the spring is in a Kelvin model is subjected to a creep load. What is the strain response in percentage when time is equal to the relaxation time? So this is the key hint to solve this problem. So it's given in this question, like one thing you it's given that ratio of applied stress and elastic constant of a spring is unit. So here you it's the sigma naught by E equals to 1. It's so for Kelvin, we know. So for Kelvin model, it's given like a so sigma naught by E1 minus e to power minus t by tau. So in that, sigma naught by E is given U1. And the another hand is given the question that when time is equal to the relaxation time. So the another hint is given is T is equals to tau. So when you sigma naught by E, when you know T by tau, first one T equals to tau, then T by tau T will be 1. So by putting these two values, you can get your strength. And in this question, you have to be submit your answer. You have to submit your answer with percentage. So if you come section, in decimal, you have to multiply this by 100 and you have to submit your answer. So there was also question in we are in the quiz we asked from three parameter based polymer model in which it's a given to you a free spring stiffness of free spring is given to you and the spring that is parallel with the damper has a stiffness that is given to you. So for three parameter model this is in the from that way. Okay. So you have given in this question E1 free spring and E2 for the spring that is parallel with the damper and the viscosity of the damper. This is the thing that's given to you. And in that question, it's asking for find a strain response if the polymer is subjected to a constant stress of 25 kilonewton. So the constant stress is 25 kilonewton. So here it's asking for strain at a time when T equals to 10 seconds. So for that three parameter model, we have formula like for strain in three parameter model, it's sigma naught 1 by E, that is obvious, due to free spring plus 1 by E2, 1 minus e to the power e to the power minus t by tau. So this first portion talking about sigma naught into sigma naught by E1, so that is for free spring. For the inputs is same, so the same sigma naught will multiply to this second section, and that will give you the strain for this parallel combination of strain, spring and damper. So it is given to you tau again. We can get this tau by using the relationship tau equals to mu by E and solve this problem. And similar question is given for the next in which we are asking for a four parameter model. So in that question, actually what happens? Question approximately same. Spring, dampers. That doesn't matter like damper, maybe left side, right side, it's not a problem. Can be the similar questions. This can be solved by the Maxwell and this can be solved by the Kelvin. It's given you E1, mu1, E2, and mu2. And here is the slide into this. So it's given to you E1, E2, mu1, mu2 given to you. And for a four parameter model, we know the formula we know strain for four parameter model is sigma naught 1 by E1 plus T by mu. So this is for Maxwell model in damper and spring connect in series. And in which we add that this, because four parameter model, Calvin model and Maxwell model is both are added together linearly. So this is one chain of these two added in that, and that is we know like 1 by E2, 1 minus E power minus T by tau. Again, tau we can calculate by using tau equals to mu by E. Okay, so this is how quiz 1, quiz 2, and quiz 3 will get solved. And if I'm talking about your major exams, so similar type of question you will face in your final exam. Final exam. And if you have any queries, then you can feel free post your questions to the question answer forum in NPTEL lecture. Like I think talking about the questions you send us. So just give me a second. I'm just opening the question that a few of you asked in the question answer forum. So just give me a 2 minutes. So there are a few questions from the question answer forum, and one of you asked that when CH3 group attached to a carbon rather than hydrogen, compact packing become difficult. That's why it's become lighter. So the question was, so one of you are asking like since there is a CH3 group attached to carbon instead of hydrogen, polyethylene, so how it can be lighter? Can you just explain? So what happens in that case? Like the professor give a very good example in the same lecture when he was talking about like simple. We can take an example of tissue paper or sometime for if you know you go a little bit like that print paper for bill. It's properly rolled there, so it take a very small space and it's compactly packed. But once we just yeah. Like we can use a simple example like if we have a newspaper, okay, it's properly compact packed, so take a small space. But if we just open every page and just make bundles of that, then it will take a very large you can say space. So the reason like the CH3 group attached, so that that may be the reason for change or other things. Like when history group attached to the carbon rather than hydrogen, compact packing become difficult. That's why it's become like that. It's the packing that responsible for the density. Okay, for deeper understanding, you can go to the professor lecture. He explained very well in that. Okay, there was another who was asking for what is MER unit. So MER unit is just a single unit like for construction of a house we need a brick. So similarly you can assume it's a repeating unit in polymer like when multiple MERs join then it becomes a polymer. Ah, someone was asking like why primary bond use large amount of precision. So it's obvious like primary bond are stable and strong compared to the secondary bonds. That's why it's require high amount of large amount of dissociation energy. And dissociation is the energy required to separate two molecules. So if the bonding is strong, then we need more energy. If bonding is weak, then we always need a low. So someone was asking like how to measure decision energy. So for that measuring energy, there are a lot of experimental and computational technique like spectroscopy, calorimetry, but that all is not the part of this course. In this course, we are only talking about relative dissociation energy, how we calculate it. Like he was also asking like can we use for biopolymers? So we can use this for different cases, maybe or maybe not. We has to give the books and remedies. So that's not the scope of this course. Oh, so someone was asking like, can we download notes of these lectures? So no, you can't download the note of this lecture. If you want, you have to go through your tutorials, make your own notes, the professor share in slides and everything. You discuss, so you can make your own notes. And one more thing, like I found most of the time when you guys have the problem, you post the question, the question answer forum. So I don't know why, but generally you guys mention the time location for the for your query. So I found that is the end of that lecture. So whenever you have to ask a question, please mention the correct location of the time. Okay. Okay. Just give me 3 minutes, then we will continue. So someone asking like WLF equation is strictly used for the temperature above glass sensing temperature and RNA source. So if the condition with the WLF equation is designed in such a way that like it can only be used like similarly if we have can say we have many relationship like that comes with a specific condition that you can use it only up to certain conditions. So in that way it's fine. But this is not the problem with RNS equation. RNS equation you can either use for above glass sensing temperature as well as below glass sensing temperature. Because most of the people, WLF equation gives the result at above glass sensing temperature. So when generally people has to solve the problem above the glass sensing temperature, then you either suffer double level equation. But in case of below the temperature, below the glass sensing temperature, it generally goes with RNS equation. Okay. So in DMA dynamic mechanical analysis, uh, this is the way from where we can people can get the value of TG. So either you can get this from the peak of 10 delta or from storage modulus or from loss modulus. So from all these three, you will get the different value. So that doesn't means that any one of them is important. Yes, all are important. All are accepted, but people usually prefer to calculate this by a peak of 10 delta method. But it's like if you have the value, if you have to report the value, then at that time you also has to be mentioned that by using what method you find this value. So this is the issue, nothing else. So this is the all just remain. So now we discussed quiz one, two, three, and also we discussed with the student post question on question answer forum. So any one of you have any doubt while scrolling the lectures and the PPT, so you can put your question either in the comment box, and it's better to post your question on the student portal. So if you post the question there, so the other student who get the same problem can see the answer supplied by us in that portal. So thanks. Okay. See you next interaction session.